Hi everybody, welcome back. Today we're going to be talking about distance on the coordinate plane. So we can find the distance between 2 points on a coordinate plane by counting when the points are directly above or next to one another. Otherwise, we can use right triangles and the Pythagorean theorem to help us find the distance. So let's take a look at example 1. So in example 1, we're going to find the distance between the points 2, -2 and 11, 10. So let's go ahead and plot those points first. Now, in case it's tough to see, here is the origin. Here is 0, 0. So just in case that's tough to see, I'm going to mark it on my graph for you. So 2, -2. So I'm going to start at the origin. I'm going to go to the right 2 for my x, down 2 for my y. So here's 2, -2. And for 11, 10, I'm going to go, again, starting at my origin, to the right 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then up 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now, you'll notice that unfortunately, these points are not next to each other in the sense that they are not horizontal or vertical. You can see that they do lie on a little bit more of a diagonal away from each other. So to find the distance between these 2 points, we're not just going to be able to count right or left or up or down. So we are going to use the Pythagorean theorem here to help us with this distance. So the first thing I'm going to do is I'm going to connect these points. I'm going to connect with my red color here. And again, use a ruler to get a nice straight line if possible. I am going to draw freehand, so I apologize. Mine might not be super perfect. Okay. All right. Now, in order for us to be able to use the Pythagorean theorem, I need to draw in all 3 sides of a triangle. So I'm actually going to put in the legs of the triangle. Oh dear, hang on. Let's put in the legs of the triangle. These are going to be blue. Let me see if I can. Oh, good. This is going to help me. All right. And then let's put the other leg in. This one I need to move up a little bit. Okay. So here are my legs. Hopefully you can see them in blue. All right. So now we've created this nice right triangle. You can see that the right angle is in this bottom right corner here. Okay. And what we're going to do is we can get the distance for our legs by counting. So notice that we can actually tell what the distance is if we count down. So starting at this top point here, I'm going to count, I'm going to count down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the length of that side is 12. I can find the length of the other leg as well, once again, by counting to where the 2 legs meet. I can start at the right angle. It doesn't really matter where I start as long as I count horizontally this time. So I'm going to start 1, 2, 3, 4, 5, 6, 7, 8, 9. So my legs have lengths 9 and 12, which means I'm looking for the hypotenuse, which I'm just going to label C. So going to the Pythagorean theorem, just a reminder of what it is: a squared plus b squared equals c squared, where a and b represent the legs and c represents the hypotenuse. So plugging in my values here, and you can put 12 first if you wanted to and 9 second. That's totally fine. I typically just start with the smaller of the 2 legs as my first value or my a value. Okay, now simplifying, 9 squared, 9 times 9 is 81, plus 12 squared, 12 times 12 is 144, still equals that c squared or side squared. All right, adding together 81 and 44 is 225, gives me c squared. And to get the value of just c, so to undo that squared term, I'm going to square root both sides. So the square root undoes the squared term, leaving me with just c. And then the square root of 225, remember we do typically get two answers for that, a positive and a negative value. In this case it would be positive and negative 15. However, since we're talking about a length for a figure, we're only going to concern ourselves with the positive value. So in this case, the distance between these 2 points is 15 units. Okay, so that's how we can use the Pythagorean theorem to help us find the distance between 2 points. So let's keep practicing. Taking a look at example 2, it says a parallelogram has coordinates A, B, C, and D. Find the length of each side of the parallelogram. Okay, so let's start by graphing. So once again, I'm just going to mark off my origin here for you. It's right here, in case you can't tell. I know some of the lines are dark on my screen. So I'm going to go ahead and start plotting some points. So A is at negative 8, 2. So starting at the origin, I'm going to go left 8, 1, 2, 3, 4, 5, 6, 7, 8, negative 2. And this is point A. Now we're going to label our points. B is 4, negative 2. C is 10, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. Here's C. And D is negative 2, 6. Negative 2, 1, 2, 3, 4, 5, 6. Okay. All right, and I'm going to connect these to make my parallelogram. Might be better for me to just draw these freehand here. Okay, I tried to use the line key, but there we go. And then here and here. Okay, so there's my parallelogram. Now, we are able to count two of the sides. So AB and CD, we can count to come up with the length of those two sides. Now BC and DA, seeing that those are on a little bit of an angle, we won't be able to count the length for those two sides. We are going to have to actually use the Pythagorean theorem for those ones. So let's first find the lengths of the sides that we are able to without the Pythagorean theorem. So AB, if I count from point A to point B, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's a distance of 12, or I should say a length of 12. From C to D, starting at C, counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, once again, which makes sense because this is a parallelogram. All right, so now let's take a look at A and B. So A and B, we're going to use the Pythagorean theorem, but in order for us to do that, we're going to have to draw in our right triangle. So I'm going to take point D, or I'm going to start at point D, and I'm going to draw a line straight down until I hit line AB. So I'm just creating a right triangle here. Okay. So here's my right angle. you'll notice that line that I just drew ends up being one of the legs of the right triangle, and I can figure out the length of that leg by counting. So 1, 2, 3, 4, 5, 6, 7, 8. So right here, this has a length of 8. Now the other leg is right here. So this leg was created by going from point A to where that line from point D hit AB. Okay, so these are the two legs that create that right angle in our right triangle. If I count the length of this leg starting at point A, I get 1, 2, 3, 4, 5, 6. So here's where our two legs intersect, and here are their lengths. So now to find the length of side DA, I'm going to use the Pythagorean theorem, and the length of side DA ends up actually being the hypotenuse. So plugging in my legs into the Pythagorean theorem, I get 6 squared plus 8 squared equals, and I'm going to say side DA squared. All right, so 6 squared is 36 plus 8 squared, which is 64, gives me side DA squared. All right, so 36 plus 64, that gives me 100, equals side DA squared. And to get the length of side DA, I'm going to square root both sides, and I get 10 is the length of DA. Okay, so side DA has a length of 10, and you know what? That's going to be the exact same thing for side BC. Oops, and I just wrote it in the BC spot, so there you go. All right, and the way you can verify that, so if we were to look at side BC, and I were to once again create a 90-degree angle. So here, if I were to take point B and extend a line from point B to side CD, okay, and stop when it intersects it. Okay, so you'll notice a right triangle is created here. And each leg, again, if we look at the measure of each leg, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6. So same as when we were trying to find the length of DA, so we don't have to do any additional math because we are going to get the exact same value for BC that we got for DA. Now, the next question, so it's just a little follow-up question. It says find the perimeter of parallelogram ABCD. So remember, whenever you're looking at the perimeter wants you to add all the sides together. So we're going to add AB plus BC we're going to add all these sides plus CD plus DA. We're going to add them all together, and that's going to give us our perimeter. So 12 plus 10 plus 12 plus 10 gives us, let's see, 12 and 10 is 22, plus 22 is 44 units for the perimeter. Okay? All right, on to the back. So now, let's plot an isosceles trapezoid. So an isosceles trapezoid has coordinates MATH. Oh, isn't that nice? Find the length of each side of the figure. So let's go ahead and do that. So once again, here's where the origin is, just in case you can't see it well on your paper or on my screen. Plotting the points, -9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6. Here's M. A is at 8, -6, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6. T is at 4, 7. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. And H is at negative 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Here's H. Alright, so doing my very best to draw in these lines. Again, hopefully you guys are using a ruler or some type of straight edge to make it look a little nicer. Okay, that guy is very, very crooked. Alright, so you can see, once again, kind of like with our parallelogram, two of these sides we're going to be able to count the length of, but the other two sides we're going to have to do a little bit of work with the Pythagorean theorem to find. So the two sides where we're able to count the length are MA and TH. So let's go ahead and do that. So counting from point M to point A, oh goodness, this is not a very good trapezoid, I apologize. Alright, so counting from M to A, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so from M to A, it's 17 units. Now, from T to H, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Now, AT and HM, this is an isosceles trapezoid because those two side lengths are the same. So to find one of those side lengths to start, let's go ahead and create a right triangle. So I'm going to work with M and H just because they're closest to me right now. I'm going to draw a line from H down to line MA, or down to side MA. And once it intersects that side, I'm going to stop. Okay. And then from that intersection over to point M, I'm going to draw another leg or another side. So here's my right triangle using side MH as the hypotenuse. You'll see we created the two legs, and we can count to find the length of each of these legs. So first, just going along the bottom here horizontally, from point M to the intersection of the legs, I get 1, 2, 3, 4. So this has a length of 4. Now counting upwards from that 90-degree angle to point H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So once again, we're looking for the hypotenuse, which is side MH. So let's go ahead and plug in to the Pythagorean theorem. And I'm going to say, they labeled it HM, so we're going to go HM here on our worksheet. Okay, so 4 squared is 16, plus 13 squared is 169, equals side HM squared. Okay, so 16 plus 169, that's 185. Now I know for a fact that 185 is not a perfect square. So when we square root this, we are going to get some type of decimal. So here's what I want us to do. I'm going to have us round to the nearest tenth. All right, so go ahead, go to your calculator. For the square root, don't forget it's second and then that x squared key. Type in 185 and you should come up with, it looks like approximately, if I'm rounding to the nearest tenth, approximately 13.6. So we're going to call HM, or the length of HM, approximately 13.6. And remember, this will also be the same for AT. Now we could have just left it as the square root of 185. We absolutely could have done that too. I'm just trying to make it a little easier for us, and we'll round to the nearest tenth. Okay, so once again, let's take this a step further and find the perimeter of the trapezoid. So remember, perimeter means we're going to add all the sides together. So 17 plus 13.6 plus 9 plus 13.6. So let's go ahead and do that. So 17 plus 13.6 plus 9 plus 13.6. And that gives us 53.2 units for our perimeter. Okay. And again, this is approximate. I should say we're not going to put the approximation sign just because we're using 13.6 here, but this gives us a good idea as to what the perimeter would be for this isosceles trapezoid. All right, let's look at example 4. A kite has coordinates K-I-T-E, EK equals KI, and TE equals IT. Okay, so that's good to know. Find the length of each side of the kite. All right, we can do that. So starting at the origin, which is right here, just in case you can't see it well on your screen, let's plot these points. So -1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's point K. I is at 7, 3, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. I, -1, -9, 1, 2, 3, 4, 5, 6, 7, 8, 9. T, and -9, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. E. Okay, so to the very best of my ability, let's connect these points. Oh dear, I don't know what that was. I think I put my arm on something. There we go. I don't like this one. All right. So we're going to go ahead now. Unfortunately, we are not able to count any of these sides. These are all on a little bit of a diagonal for us. There's none that are horizontal from each other or vertical from each other except for EI and KT, but those are not side lengths that are part of the kite, so we won't be able to count those right now. So we're going to have to come up with a different way for us to figure out these lengths. So what I'm going to do is I am going to start kind of creating some right triangles here. So the first thing I'm going to do is to find side KI. I'm going to create a right triangle where, starting at point K, I'm going to draw a vertical line down to meet where point I is located. So what I mean by that is, starting at point K, I'm going to draw a vertical line until it reaches, I should say, until it's directly horizontal from point I. And then from there, I'm going to draw a horizontal line over to point I. So you'll see what I did was I drew in two legs which intersect at a point and create a 90-degree angle. So now these two legs I can actually count and get the length of. So let's do that. So from K down to the intersection, I have 1, 2, 3, 4, 5, 6. So a length of 6. And then from that right angle over to point I, 1, 2, 3, 4, 5, 6, 7, 8. All right. So let's go ahead. Using the Pythagorean Theorem now, we can find the length of side KI using these two legs that we just drew in. So let's go ahead and do that. So 6 squared plus 8 squared gives us side KI squared. All right, so 36, 8 times 8 is 64, is KI squared. All right, 36 and 64, that's 100. Again, set equal to ki squared. And when I square root both sides to undo that squared term, I get ki equal to 10. All right, we can do that. Now, we were told at the beginning that ki and ek are equal. Okay, so ki and ek then both measure 10. All right, now we've got to find TE and IT. Now, once again, these are going to be the same value, so as long as we find one of them, we'll be in good shape. So I'm actually going to find IT, and the reason for that is I'm going to be using that intersection point. So this point right here, let's see, I'm using this point right here to help me create another right triangle. So instead though, I'm going to, from that point, I'm going to extend a line vertically down to point T. So you'll notice by doing that, I've created a leg and another right angle. And now you see I have another right triangle that I'm creating in green here using one of the legs from the original right triangles that I created for ki and drawing in the other leg. So let's see, what is the distance of this new leg that I just drew in? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This guy has a distance of 12. So the two legs for this particular right triangle measure 8 and 12, and our goal now is to use those legs to help find the value of the hypotenuse IT. So I'm going to come down here a little bit and do this work. All right, so using the legs here to help find the length of IT, 8 squared is 64. Plus 12 squared, 12 times 12 is 144, and that gives me IT squared. 64 and 144 give us 208. Okay, so I know for sure that 208 is not a perfect square. So when I go to my calculator and I square root 208, so second x squared, 208, I'm once again going to round to the nearest tenth just to make our life a little easier. So the square root of 208 rounded to the nearest tenth here gives us approximately 14.4. Approximately 14.4. Okay, so let's use 14.4 as the length of IT as well as TE. Okay. All right, now it says draw EI and KT. All right, so E to I and K to E. So if we draw in those lines there, so from E to I know we have a lot of colors going on right now. And really, K to T, we've already done. We have already done that. There we go. And we're going to label the intersection point R. So that was that point that we used to help us. So we're going to label that intersection point R here. It asks what's the coordinate of R. Okay, so looking at, I know, and this is why I wanted to put in our origin here. So from our origin, R is located at -1, 1, 2, 3. Okay. So now what we're going to do is we're going to find the area of the kite. Okay, we can do that. So in order for us to find the area of the kite, I'm going to use all of these triangles that we drew in to help us figure this out. Okay, so I'm going to find the area of each of these individual triangles. You'll see that there's actually 4 triangles right now that have been created. Once we drew in EI and KT, we had 4. So I'm just going to quickly show you the 4 triangles. I'm just going to write them down. So here's the first triangle, which is what we used to help us find the length of KI. And directly next to it is a second triangle that's basically the exact same as the first one that we drew in. This third triangle right here is a match for the fourth triangle, which we used to help us find side IT. So there's 4 different right triangles all located within this kite. I'm going to find the area of each of these and then combine them for the overall area of the kite. So let's look at that first right triangle that we labeled. So it's KRI. Let's look at that for a second. If I'm trying to find the area, remember the area of a triangle is 1/2 base times height. So A equals 1/2 base times height. Now for this particular triangle, the base is represented by side RI. So I have a base of 8 and a height, which is represented by RK or KR, which is 6. So A equals 1/2 base times height. All right, so multiplying straight across here, 1/2 of 8 is 4, and 4 times 6 is 24. Now that helps us with triangles 1 and 2 that we have labeled. So the area of triangle 1 and the area of triangle 2 is 24 units. Now let's go ahead and find the area of triangles 3 and 4. These areas should be the same. So once again, using the formula for area of a triangle, 1/2 base times height. Looking at triangle number 4, just because I have everything labeled there, looking at triangle number 4, my base, you could say, is 8, and my height, you could say, is 12. So let's go ahead and plug in those numbers. And it doesn't matter if you switched them up, that's okay. We will still come up with the same answer. All right, so once again, 1/2 of 8 is 4, and 4 times 12 is 48. So here are the areas for each of the 4 triangles. So triangle 1 and triangle 2 each have an area of 24 units. Triangle 3 and triangle 4, since they are the same, each have an area of 48 units. So now to get the area of the kite as a whole, I'm going to add all of these together. And the reason I'm writing 2 24s and 2 48s is, remember, we have 4 separate triangles all within that kite. So 24 plus 24 plus 48 plus 48 gives us 144 units squared for the area of the kite. All right, let's keep moving on. We're almost done. Okay, example 5, 3 points A, B, C are plotted. Very nice. Are the points A, B, C all on the same line? Justify your answer. Well, that's a very good question. So one way we can figure this out is by going back to our knowledge of slope. Do all of these, or I should say, do the respective lines. So if we were to draw a line in, from A to B and B to C, do we have the same slope? So here's where slope triangles, or that rise over run, come into play to help us. So we're going to use slope, which again is rise over run, to help us see if these 3 points are on the same line. If they have the same slope between them, then they are on the same line. So let's take a look. So if I go from point A to point B, I'm going to rise 1, 2, 3, 4, 5, 6. So I rise 6 and I run 1, 2, 3, 4. Okay. So if I'm looking at the slope segment AB, right? So if I were to connect those guys, I would have 6 over 4, which reduced, I can divide both of those by 2, would give me 3/2. All right, now let's find the slope of BC, or between points BC. So if I'm looking at BC, to go from point B up to point C, I'm going to rise 1, 2, 3, 4, 5, 6. And I'm going to run 1, 2, 3, 4. So look at that. We rose 6, ran 4, which gave us the exact same slope. So are all 3 of these points on the same line? Yes. Because they all have the same slope. All right, and the line, so if we were to actually kind of draw in the line that they're talking about, we would connect those points. I'm going to try and use this line tool again to see if it helps me. Ooh, it is not great. Okay, maybe we'll just avoid that line tool. There we go, that's better. So here's kind of that line that they're talking about. Okay, all right, so let's move on. Is B the midpoint of the segment from A to C? Justify your answer. So if we're just looking at, so if I kind of shrink up my line here, I don't know if it's going to let me do it. Nope. Okay, you go away. And we'll do this. So if I'm just looking at the segment from A to C now, how can I tell that B is the midpoint or halfway between points A and C? So here is actually where the Pythagorean Theorem is going to help us come into play. So I want to see if the distance from point A to point B is the same as the distance from point B to point C. And you'll notice we actually already drew in some really great triangles to help us find the distance between our points. So if I'm looking, let's work on first the distance from point A to point B. So looking at point A to point B, A to B is my hypotenuse, so I'm going to use my legs, which measure 4 and 6, to help me figure out the distance from A to B. So plugging this into the Pythagorean Theorem, 4 squared, oops, I should use this in red since that's the triangle I'm using. 4 squared plus 6 squared gives me AB squared. All right, so 4 squared is 16 plus 6 squared, which is 36, gives me AB squared. All right, 16 plus 36 gives me 52, and I know for a fact that is not a perfect square. So if I take the square root right now to undo the squared term, I get AB is approximately, and again I'm going to round to the nearest tenth here just like we did before, I get AB is approximately 7.2. Now if we take a look, you'll notice that in our triangle, if I start to find the length of BC, you'll notice that I'm using the exact same leg values. I have a leg that is a length of 6 and a leg that's a length of 4. So if I plug this in, I'm going to end up plugging in the exact same equation here. Right? Here's the leg, here's the other leg. And now I would be finding the distance from B to C. You'll notice it's the exact same equation that we just used. I would get 52, or I should say that we just solved. And then you would square root. So it's looking like, based on our calculations here, AB and BC are the same distance apart, which means B is the midpoint of the segment from A to C. So let's see. So we have segment AB and segment BC are both approximately 7.2 units, which means B is the midpoint. Oop, I'm squeezing it in. From A to C. If B wasn't the midpoint, then segment AB and segment BC, the lengths of each of those would not be the same. Okay, they would be different. All right, so just to round out what we've done today, we're going to quickly find the length of each line segment in example 6, and then we'll be done. So once again, we're going to use those wonderful right triangles that we're going to draw in, very similar to our slope triangles that we've used in the past. So whichever way you want to go is fine by me. I'm going to draw my right triangle. I'm going to come down and over to create my two legs. Again, you don't want to go past either of the points that you're working with. You want to draw your line down, or you could go up if you wanted to go on the left side. You could do that too, kind of like we did when we dealt with slope. So if you would rather go kind of like a rise and a run up to where you're in line with that second point and over, that's fine too. So we went up 6, right 1, 2, 3. Here is my right angle. We are once again finding the hypotenuse, which we have labeled D here. So 3 squared plus 6 squared is D squared. 3 times 3 is 9. 6 times 6 is 36 equals D squared. 9 and 6 is 45, which I know for sure is not a perfect square. So when I square root both sides to undo that squared term of D, again, I'm going to give you an approximate here. We're going to round to 1 decimal place. We're going to say 6.7 is the length of D, or the approximate length of D. All right, and then going on to this next graph, once again, depending on how you want to draw your right triangle is totally fine by me. I'm going to come down this time and over. Here's my right angle. I've created my two legs. One of them has a length 1, 2, 3, 4, 5, 6. The other has a length 1, 2, 3, 4. And we're trying to find that hypotenuse. So 4 squared plus 6 squared is the hypotenuse squared, which in this case we have labeled D. 4 squared, 4 times 4 is 16, plus 6 times 6 is 36, equals D squared. 16 plus 36 is 52. This is what we just worked with above, equals D squared. And square rooting both sides to undo that squared term, I get an approximate length of 7.2, just like we did above. All right, we did it. Okay, so tomorrow we're going to do a little bit of review. Make sure to email myself or Mrs. Hayward if you guys have any questions.